This video is a brief summary of our final year honours project undertaken at the University of Adelaide. Is secure communications possible without a key exchange? The basis of this project was the KS cipher. The KS cipher, also known as the double padlock protocol, is theoretically known to offer perfect security through a classical information channel. However, realization of this protocol remains a difficult problem as the required mathematical operators are yet to have been found. A mechanical analogy of the KS cipher can be seen by sending a message in a chest using two padlocks. So let's say that Bob wishes to send a message in a chest to Alice. He can attach his padlock and send the chest over to her. Alice, then unable to remove Bob's padlock, attaches her own as an additional layer of security, and then sends his chest back to Bob, who can remove his padlock, and then finally send the chest back to Alice to remove hers and hence recover the original message. This technique is theoretically perfectly secure as the box was locked at all times. So in undertaking this project, we effectively sought commuting mathematical operators that could be utilized for this protocol. Now, geometric algebra is the Clifford algebra of a vector space over the field of real numbers, endowed with a quadratic form. It was taught to us in the preliminary stages of the project, as it was intended to be the majority focus for the duration of the project. It's a powerful mathematical tool and is currently being utilised in many research applications in the field of engineering and science. So our initial approach was to utilise geometric algebra, or GA, to explore the possibility of encryptions via rotations in n dimensions by stepping up through the dimensions starting with 3D, where the message would be defined as a vector in 3D space and the rotations would be performed around rotation axes independently chosen by the sender and receiver, or Alice and Bob. We will then identify possible encryption operators and then either confirm or disprove their viability theoretically with the aid of software and developed animations using cloovers. Through following the approach, it was found that rotations in 3D didn't commute, and the only circumstances under which the initial and final message vectors would equal one another was when the two rotation axes chosen were in parallel. However, in order to have the rotation axes in parallel, the sender and receiver would have to agree on it beforehand and hence communicate said information, which goes against the premise of the double padlock protocol, which aims to avoid any information regarding the encryption being transmitted. It was at this point that we moved on to 4D rotations and 5D rotations embedded in a 4D space. And after a range of difficulties with both the inherent complexities of 4D rotations and our underlying approach, it was conjectured that in order to obtain commuting operators, the operators had to be simplified to the point of an eavesdropper being able to decode them. So for this reason, in conjunction with an outlined flaw in our approach summarised with information theory, we dropped the prospect of using geometric algebra.
As we just explained, there was a possible hole in our approach as shown by information theory, because there's no mutual information in the previous approach that we were talking about. That is, if we do two independent rotations on either end, we can see that they're completely independent, which means that our ability to generate a secret key is 0. So we moved on to this new approach using round trip times, where we use the round trip times between two machines representing Alice and Bob to create a secure key. So you might ask how this works. The first step is to record round trip times forever. So we set up a loop where we just record round trip times by doing the following process. Alice sends a message to Bob, who sends it back to Alice, and then Alice sends it to Bob again. The two people are able to record their round trip times as we see in the picture. From here, we have blocks. For each of these blocks, we calculate the median of the round trip times, and then for each entry, if it's greater than the median, we return a 0, if it's less than the median, we return a 1. Using this, we're able to generate a bit stream. But at the moment, it's quite useless to us, because as I'm about to demonstrate, when we're communicating over the internet, it's not a steady channel, so these round trip times are going to be very, very different. And we have a look at this, and we can see that when we just ping a random host, each time we get a round trip time back, it's completely different. So using this as a secure key at the moment is completely useless. We need to first perform something called bit parity checks to lower our bit error rate to allow us to use it effectively. So what is this? Basically, what we do is we've got these bits and we group them up into pairs. We perform the bit parity check and we send it across the wire, say from Alice to Bob. Bob performs his bit parity check, and then if it checks out, we throw out one of the bits and keep the other one. This is to confuse the eavesdropper to stop him from getting any information. If the bit parity check fails, however, we just throw out that entire block of bits. So by doing this, we're lowering the Alice and Bob bit error rate. We can see that on this graph, it shows this. We see that the Alice and Bob bit error rate starts off about 35% and then falls to 0%. So I want to take a minute to explain this from Eve's perspective. Why is it that this is effective for Alice and Bob, but not for Eve? Basically, what we need to realize is, Eve, say she's doing a passive man-in-the-middle attack, where she's just listening to what is happening on the channel. She doesn't actually have access to communicate on the channel. Using the bit parity checks, Eve can take these and apply it to her own bit stream which she generates, but we need to keep in mind that it's not going to be that useful for her. This is because over the internet, or even the LAN network for that matter, Alice, Bob, and Eve are going to have independent sources of noise, which means that her bit stream is going to be different from Alice and Bob's, which means that these errors that Alice and Bob think are errors might not actually be errors for Eve, which means that when she performs the bit parity checks that Alice and Bob think are good, it's just not going to be as effective for her. We can see that in the example shown on the screen. So back to our results, we see that the Alice and Bob bit error rate does drop, as does the Alice and Eve one, but it's clear that Alice and Bob's drops much faster. This is just due to what I described, where Eve might be removing some correct bits, or she might be keeping some incorrect bits. In conclusion, our project initially started as us trying to find a solution to is secure communications possible without a key exchange. However, throughout the course of the project, we determined that the answer to this question is no, and we moved on to a physical layer timing-based encryption process, which focuses on generating a secure key. Initial testing reveals to us that this is an incredibly viable option. However, this is only initial testing, and many more tests will need to be conducted